Okay, time for today's class. Again, my dear young friends, thank you again for coming, for showing up on time. I appreciate your participations. But let's first review what we have learned in the previous week. Now, the reason we want to study closed-loop controls is not just for better stability, better tracking error. The very fundamental reason that we want to use closed loop, that is feedback controls, in the first place is we want to manage uncertainties, okay? Manage uncertainties. Uncertainties is something we cannot predict beforehand, okay? And it is sometimes and most likely to be random, okay? After all, as we said before, we are living in an imperfect world. Now, in this course, or in the framework of, I'm sorry, wrong page. In the framework of automatic control, what uncertainties we need to manage? Input disturbance, parameter variation, and finally, measurement noise. All right? And as we have seen, as we saw in last week, if I assume a unity feedback system, all right, and this is my process and this is my controller. G represents the transfer function of the process I want to control. And controller GC represents the transfer function of the controller that I need to design. Then it can be shown that the output, the actual output, the real output of this so-called unity feedback control system is actually this. So what the output really is depends on three different inputs. The first is, of course, the nominal input of the control system, the command of the control system, the desired, the target output of the system, all right? If everything operates perfectly, we want Y to be identical as R, at least as fast as possible. If they cannot be identical, at least we hope the difference can be somehow minimized, okay? Now, the second part is the represent the inference of input disturbance. And the final portion of the output is due to measurement noise. So in a way, this represents three different inputs. This is what we call the command or the nominal input. And these two inputs are undesirable inputs. We don't want them, but they are there. So we need to deal with them, okay? No matter we like it or not. The truth of the matter is they are always there. So we need to deal with them, all right? Now, the differences, one fundamental differences between these three inputs is that they enter into the feedback control system in different locations, all right? One come into the system here, the other is here. Finally, measurement noise enter the feedback loop control system from this junction, all right? Okay, remember here, I assume, and from now on, I will always assume unity feedback, okay? Now, because we have three inputs, okay? Therefore, we have three transfer functions, okay? As you can see from these three transfer functions, one common property of these three transfer function is that they have the same characteristic polynomials, okay? Which means these three subsystems has the same poles, all right? The difference, however, is in the numerator, all right? Is in the numerator. All right, so with this in mind, remember that, let me explain how do we get these transfer functions. The first equation that we use is based on the result of this slide. Here we have a transfer function, and by going through this mathematical derivation, we know that the ratio of the output to the input is this, G divided by 1 plus GH, which is the transfer function of this system. Okay, so based on this very concept, we can determine the transfer function between R and Y. We can also determine the transfer function between the input disturbance and the output. The only thing we need to do is go back to this block diagram and redraw this block diagram by treating TD as input and see what kind of feedback control system it is, all right? This feedback control system is different from this feedback control system, right? Why is that the case? Because TD and R enters into the closed loop feedback system in different location, in different place, all right? Or different junction, all right? Same thing happened here. By treating measurement noise as input, I can redraw this block diagram as this configuration. Again, this configuration represents that this is a feedback control system. So by using this result, which is for this block diagram, I can determine the transfer function between Y and minus N as this, okay? Now, the next thing we want to do is we want to understand the output arrow, because the output arrow is something we want to minimize, right? Because we want Y to be as close as R, since R represents the command, represent the target output, and Y, as I said many times, represent the actual output. Okay, so this represents the reality. This represents the ideal goal. Okay, the ideal condition is most likely different from reality, the real conditions. Okay, now that is inevitable, but what we can do is try to bring them together as close as possible. So the first thing we need to do here is we want to define, we need to come out with a function to represent the difference. And this is such a measure, okay? This represents output arrow, which is defined as the difference of R and Y, all right? Now, since we already know what Y is, right? From here. So by substituting that representation into here, this is what we will get. All right. So the reason why we have output arrow is because of this, also because of this, also because of this. All right. The nominal input, the input disturbance, the measurement noise, they all have their contributions to the output arrow. Okay. Now, let's look at a possible way. Let's study how to find a way to minimize or to reduce at least this output error. One simple strategy is, oh, I forgot to mention that here L represents the loop transfer function, which is the product of the transfer function of controller and the transfer function of process. Okay, so L is equal to the product of GC and G. Okay, this L is equal to GC times G. All right. So one simple way to reduce G is to increase L, right? Because when L increases, the denominator, the denominator of all these three terms increases. As a result, the contribution of these terms to the arrow decreases. All right? So one simple way to reduce the steady state arrow or to reduce the output arrow is simply increase L, that is, increase the loop transfer function, the gain of the loop transfer function. Okay, but it is actually not that easy. All right, why is that the case? Let me rewrite this transfer function, this representation. Okay, here I will introduce two additional functions. One is S, the other is C of X. Okay, X is defined as 1 over 1 plus L, whereas C of X is defined as L divided by 1 plus L. The reason, but by introducing these two new terms, these two new functions, this equation can be rewritten as this, right? This is nothing but S, right? Here, this is S, but you need to multiply G with S, right? And here, this is, of course, this is S, but actually, we need to look at this term as a single term, which is C, all right? So this equation now is written in terms of S and C. The reason we want to do that is we noted that based on the definition of C of X and C of X and X of X, we know that based on these two representation, we know that their sum has always equal to 1, which means if the value of X go up, C has to go down, vice versa, all right? Now, what does that mean? It means that, let's say I want to increase L, all right? If I increase L, when L goes up, then X goes down, and then C goes up, okay? Why is this the case? Because of this equality, okay? Now, when I increase L, S go down, this term becomes smaller. This term, because it has an S here, it will also become smaller. However, when S go down, C always go up, and this will increase. So apparently, we need a trade in tuning the magnitude of L. There is a trade-off in selecting the size of L, all right? Because if you make this term smaller, this term will become larger, okay? Now, why is that the case, okay? Of course, I can tell you that that's what mathematics tell us, okay? This is a fact that can be proved, that have already been proven by using pure mathematical technique. But the reason is that, the real reason is that the state error come from the input disturbance, and the steady state, the output error come from the measurement noise. They represent two different kinds of uncertainties. The reason why we can reduce the impact of input disturbance by increasing L is by increasing L. Okay, we remember the entire spirit of feedback control is arrow driven. Okay, the arrow is here, and the arrow will be multiplied with GC and then G. That is, the arrow will always be multiplied with the loop transfer function. If I have large L, that means the controller will produce stronger, larger corrective action to try to minimize or at least reduce the error. Okay, so that is why increasing L is useful for reducing this as well this, because when you increase L for the same error, the controller will produce stronger, larger corrective action to try to reduce the error. Okay, but why this strategy doesn't work for these terms? As a matter of fact, if you increase L, let's say to infinity, this term will become 1. Okay, and the entire measurement noise will become a part of the output arrow. So nothing has been done on output arrow. Okay, now, the reason why that the strategy of increasing L doesn't work is that the very reason why it can work is because the action produced by the controller depends on the output arrow. However, if I have measurement noise, that means this output arrow is actually incorrect, all right? Because this is not real, okay? In addition of Y, what the controller is getting is an additional N. I'm sorry, an additional, I'm sorry, should be a minus sign, additional M, right? Because Y is here. If there is no arrow, Y, we already assume that H is equal to 1, enters into this junction, okay? So R minus Y is output arrow. However, if I have a measurement noise here, then the measurement noise will also follow this path to meet with the nominal input. As a result, the arrow will have additional terms. Okay, remember, our feedback control system is arrow driven. Okay, by increasing L, controller will produce stronger, larger corrective action to try to minimize the output error. But such a strategy will backfire if this error is inaccurate, right? The stronger action, the stronger my action is, the stronger negative result I will get. If the information where my action is based upon is incorrect. Okay, if I do something based on correct information, okay, I can expect good result. If I do something based on incorrect information, things will probably get worse. And the stronger my action is, the worse the result. Okay, because the information where my decision is based upon is incorrect. That is the reason why I cannot reduce these two errors simultaneously by simply adjusting error. All right. So choosing transfer function is balancing a balancing act, balancing between these two kinds of errors. Now, how do I balance that? The solution is I can have high, low frequency gain, which can improve tracking and disturbance rejection. Remember that L is not a number. L is a function of X. And by setting X equal to J omega, we go from X domain to frequency domain, which means the loop transfer function is a function of frequency. So in reality, you can think of the loop transfer function as another subsystem. All right. Now, since you can think of it, you can treat it as a subsystem. Of course, such a subsystem has its own frequency response. Okay. Now, so in dealing with these two terms, what I can have is the transfer function. I'm sorry. The magnitude plot of my L can look like this. Okay, this here is 0 dB. For this part, this is reserved for here. Okay, I will make my L it's not 0 dB. Make it very, very large and make L very, very in low frequency. All right, so that TD, the contribution of the input disturbance, can be reduced. Okay, and by making L very small in the high frequency band, I can somehow reduce the impact of the measurement noise. So low frequency gain improve tracking and disturbance rejection. Okay, tracking error comes from here. Disturbance error due to input disturbance is here. Okay, while low frequency gain is needed for noise reduction and robust stability. All right, I can make error so small in the high frequency band to reduce the impact of the negative inference of measurement noise. Now, so the trade-off when selecting the size of L have everything to do with the frequency contents of the noise. Okay, and so let's briefly summarize what we have learned. What we have learned, the first thing is that we want high gain at the low frequencies, so that system can track the reference well and reject disturbance. That is, reduce these two error terms. You want low gain at a high frequency, so that the system is not sensitive to the noise and stays stable and robust, which means by making L small and therefore C small, I can somehow reduce the impact of the measurement noise. The reason why this is the case is that most noise sources arise from rapid random physical fluctuation, okay, such as electromagnetic interference, switching, circuit switching, vibration, all right? So this phenomenon naturally generate high frequency components. So the energy of most of the real noises actually are concentrated on the high frequency bands, okay? It has relatively small energy components in the low frequency band, okay? So if, let's say, it has 0 energy components in the low frequency band, then if I multiply it with a very large number, it really doesn't matter, because no matter multiply what number with 0, you always get a 0, okay? So most real world noise tend to have greater energy in the high frequency bands, okay? Now, this is also one of the reasons why we need to talk about frequency domain and analytical techniques, because without that kind of understanding, we cannot explain how to select L to balance the impacts of input disturbance and measurement noise in designing a controller. Now, the last uncertainty we need to address is parameter variation, okay? Now, how do I study parameter variation, okay? Because it is not like input disturbance and measurement noise. It is not a signal, okay? So I cannot represent parameter variation as an input to my feedback control system, okay? So I need to represent parameter variation as a modeling error. How do I do that? Now, here, this is the error. Now I assume I don't need to consider input this. What's the matter with me? I assume I don't need to consider input disturbance. I do need to consider measurement noise. The only error term I need to consider is this, all right? Because let's deal with uncertainties one term at a time. Okay, now without any input disturbance, without any measurement noise, this is the error of my feedback control system. Now, assuming that I have parameter variation. So what really happened is, what happened is the G is the transfer function of the process that I need to control is not G. There is some, due to parameter variation, there is some modeling error. So the real transfer function of the model, let's just assume is this, G plus delta G. And the delta G apparently represent the difference between the real transfer function and the mathematical model of the transfer function that I use, okay, of the process to be controlled. So because of this, I have another error term, okay? Then, and let's just assume this new error term as delta E. What I need to do is I need to reduce this as much as possible, because I can reduce this by increasing GC, right? Now, the next thing I need to do is, of course, reduce this as much as possible to counteract the impact of parameter variation. Now, to do that, the first thing I need to do is to understand what is this additional error is made of, all right? What it is, what is its components, what make it larger, how can I make it, what make it larger, okay? So to do that, all I need to do is subtract 1 from 2, right? Because that will give, by subtracting E from this E plus delta E, what I will get is, of course, delta E, okay? So by using the right-hand side of these two equality, I have this term, okay? The first thing I need to do in getting this result is I multiply both sides. I multiply this side with this, so that these two terms will have the common denominator, all right? Similarly, if I do that to the denominator, I need to do that to the numerator, all right? Same thing happened to equation 2, okay? I need to multiply the denominator and numerator with this, okay? Now, if that is the case, this is what I will get, all right? Now, after going through some mathematics, okay, we know that the numerator will become this, because this cancel out the other, and this 2/10 cancel out the other. So the only remaining term is this times this, which is GC times delta G, okay? And the denominator is same as this, okay? Now, for the time being, let's just assume G to be larger than delta G. So here I assume the parameter variation does exist, but it is not that large, all right? So if this is the case, I can rewrite the denominator. I can, neglecting this term, as a result, the denominator can be rewritten as this, all right? Okay, so this is the error due to delta G, okay? Again, let's assume L represents the loop transfer function, which is GC times G. Then this result can be rewritten as this, all right? Now, let's assume again that L is much larger than 1, all right? Then if this is the case, then 1 plus L is approximately L, okay? Because L is a very large number. Then this representation, again, can be simplified as this, okay? Now, here, remember that L base definition of L, which is the product of GC and G. I can now rewrite this this representation as this. Okay. So what does it tell us? Of course, the first thing I know is that I get what I want. Now I know what is this arrow made of. And remember, my goal is to make it as small as possible. After all, it represents the negative impact of parameter variation. This is an additional error term due to the uncertainty of parameter variation. I don't want it, okay? Now, the first thing I noticed that I can make it small by increasing L, okay? That's good, because by increasing L, I already can reduce the error due to the nominal input. Now, by increasing L, I have another benefit. That is, not only I can reduce this error term, I can also reduce this error term, a win-win situation, okay? Now, the other thing I notice is that this error is actually proportional to parameter variation, all right? Which means if delta G is larger, then delta E is larger, okay? Does that make sense? It makes a lot of sense. That means if I have larger modeling error, which means I have larger parameter variations, then I should expect larger error due to modeling error, okay? As a matter of fact, it is not just delta T, it is not delta G that is proportional to delta E. It is actually this, the relative error, okay? Not just the absolute size of modeling error, but the relative size of the modeling error, because here you need to divide delta G with G, all right? So let me summarize what we have learned here, okay? Parameter variations, high blue game, that is large L value, drastically reduces the sensitivity to closed loop error, due to brain game variation. However, high loop game can introduce side effects. Up to now, we have talked about a lot of good things about increasing L, how increasing L can reduce my error. However, there is a catch. There are some side effects we need to be aware of. Tend to make the system respond more, because when I increase my L, it tends to make the system respond more aggressively, right? Okay, because as I said, L is here, and the output, it will multiply the output to generate the final it will multiply the output arrow to generate the output. The larger the loop gain, the more aggressive this corrective action will be, all right? So it will, by increasing L, I'm sorry for this mess, okay. By increasing L, okay, we tend to make the system respond more aggressively, okay? The key word is aggressive, all right? You make larger overshoot and often longer settling time, okay? Now, and it requires more aggressive controller output, which can lead to actuator saturation, all right? Every actuator has its limits. A motor can only produce limited amount of torque, all right? An engine can only produce limited amount of force, all right? So a motor can only rotate to a limited speed, rotational speed. There is always a limit. By using large loop gain, if it means I require the actuator to produce more, and that can lead to actuator saturation. That means the required output, my demand from the actuator output is something the actuator cannot satisfy, okay? And by increasing loop gain, it will also reduce my stability margin, okay? Let's say this is the original body diagram of my system. Now, the L, the loop transfer function, let's just assume for the time being is K times G, where G is the function, is the process I want to control, and K represent the controller, which means I'm using nothing but a proportional controller. This represent GC, all right? And it is apparently a proportional controller, all right? P controller. Now, if I let's, for the sake of discussion, let's just assume originally K is equal to 1. And this is magnitude plot. This is its phase plot, okay? When K equals to 1, based on the definition of phase margin and gain margin, the first thing I need to do is, let me locate the gain crossover frequency and then go down to the phase plot to see what the phase angle is and how far away this angle is from the minus 80 degree. And such a margin is what we call phase margin. Similarly, to determine gain margin, I need to go to the phase response and determine the so-called phase crossover frequency, okay? I go to the frequency response and see what frequency is when the phase is minus 180 degree. And then I go up to the magnitude plot and to see how far away the magnitude is from 0 dB. And this distance or this difference is what we call gain margin. Now, if I increase K from 1 to, let's say, K from to 10, okay, then what is really happening is the phase response curves remain unchanged, but the magnitude plot will elevate without the shape remain the same, but the entire curve will elevate horizontally up, all right? And based on the result of this elevation, you will see that the gain crossover frequency shift from here to here. And the result is the phase margin therefore becomes smaller because at a higher frequency, my phase response has smaller angle, all right? Same thing happened to the gain margin, okay? Now, the phase margin remained the same, all right? I'm sorry, the phase crossover frequency remained the same. But the thing is, when I elevate the magnitude response, the magnitude plot, the gain margin naturally becomes smaller. And that means gain margin goes down, phase margin goes down. Okay. The department need to do an evaluation. Okay. And 现在要做一个教学评量了哈，那这是系上要做的哈，麻烦大家配合一下。那我们就他们做完以后，10点10分回来 ，I'll come back 10 after 10 after this survey. All right.
结束之后，我都会到隔壁陈老师的班试测这样子。
OK， 好，没问题。不好意思。